Hi, my name is Matt Holliday. Welcome back to my class. In this segment, I want to talk about functions. And when I talk about functions, I also want to talk about how parameters are passed to functions. And then I want to introduce a new statement called defer, which is a very useful way of making sure when a function is done that certain things get done with it. So let me start first by just pointing out that functions in Go are first-class objects. And what we mean by first class is you can do almost anything with them, right? This hasn't been true in traditional languages. If you're accustomed to functional programming languages, then you've probably seen this already. But in some traditional languages, you can create a function by name and you can call it, but there's lots of things you can't do with it. And in Go, you can do almost anything with a function that you can do with an integer or a string. You can assign it to a variable, you can pass it as a parameter, you can return it as the return from a function. So we can make functions that return functions, and we're going to find that's very useful. And the next thing I want to mention is function scope. So we talked about package scope and function scope, and pretty much everything that you can declare in a function that you could have declared in a package. So you can declare types inside a function, variables, constants, and you can declare other functions within a function. Now, functions have what's called a signature. And what we mean by signature are the order and types of its parameters and its return type. Okay? The name of the parameter that we give when we declare it doesn't matter because that's really local to the function. What matters are the types that we give the parameters and that they're in the same order. So if I have a function that takes an int and a float and returns an int, that's different from a function that takes a float and an int in that order and returns something, right? So it's not just that you have three parameters, it's that you have three parameters of a certain type in a certain order, and then again, that the returns are also matching. And this gets back to structural typing. Functions are always done with structural typing because we don't normally have function types. We can, but we don't normally have them. And if we apply the name type rules, then we have a very hard time actually using functions as first-class objects. Now, when we talk about parameters, I want to use a couple of terms because they're kind of important so we can all be on the same page. And the first is the notion of a formal parameter. So when you declare a function, right, in the declaration you're listing what are called formal parameters. So if I look at the declaration of function do, a and b are the formal parameters of the function. And the reason we use that term is because when you call the function, the things that you pass in, which are sometimes called parameters or arguments, those are the actual parameters. And they're specific to an individual function call, right? So the declaration has formal parameters and the call has actual parameters. Now, we also have a couple of other terms, and that's the notion of passing by value or by reference. And the model here is if I pass something by value, I'm copying it. So you get a new copy of the data. And if I pass something by reference, then what you get is like a pointer to it, but the data is the same, and so the function sees the same data as was seen outside the function. Okay, so these are two parameter passing models. In history, there used to be some others, but they're pretty much dead now, right? And I want to talk about how those apply to Go, because there's a practical way of looking at it, and then there's a technical way of looking at it. In the practical way of looking at it, we tend to think of certain things as by-value parameters. Numbers, structs, arrays, because they're all copied. And then there's other things we think of as reference parameters, like slices and maps. And we're going to see that there's the practical view of it when you think about the data that's behind the slice or the map, and then there's the technical view of what actually happens when you call a function. So now we're going to go back in the playground because I wanted to illustrate some things about parameter passing. So I'm going to start with this first example. And I'm going to create a function, and I like simple functions, so we're just going to call them do. And let's see. We'll create a little array. And we're then going to assign a A. Now that means we're going to come up here and we're going to put a formal parameter on A, and it has to match. So it's going to be an array of 3-ints. And what we're going to do in here first is we're going to assign to the array, and then we're going to return part of it, right? So I've got this little function do. It takes an array of 3-ints, it returns an int, and it's going to try to do an assignment and then return a value. Fine, so good. All right, and down here we're going to have the main function. It's going to create the array of 3-ints, call the function on it, get the return value, and we're going to print the two values and see what happens. Right, and I get two things back out. So the first thing I get is the array A, and that's the one I created, and then I get V, and what we notice is A hasn't changed. So I created A with the values 1, 2, 3, and it still has the values 1, 2, 3. And when I return the value like B1, it's just the value 2. So what's going on here is that when we pass an array, the array is being copied. All the values are copied, and so B is really a different array. It's a local variable that has the values from the A array copied into it. So changing that array inside the function doesn't change the original array at all. Okay, so this is clearly a case of pass by value, right? Pass by value means you get your own copy of it and the changes you make to it are local to your function. Now I want to change this up a little bit, right? We're going to change this to a slice. And now what we're going to see is when we run it, something different happens. So B takes a slice event, A is a slice event, and when we run this, what we see now is that A has changed. So A started out as 1, 2, 3, but after we call the function, A has the values of 0, 2, 3. And the reason for that is that this assignment right here, B sub 0 gets the value of 0. Well, it changes B, but it changes A, because A and B both refer to the same array of values. Okay, and I can show that by adding a little print line in here. So actually, I'm going to do a printf. All right. And what I'm going to do, the %p is usually used to print a pointer. When you use it for a slice, what it does is it prints the pointer that the slice has within it, which is really the address of the first element. And I'm going to do that down here also before we call A, before I call V. I'm going to see here, okay, and when we do these, we're going to see that they have the same value. If I look at these pointers, A is at this address, effectively BE000, and B is at the same address. In other words, A and B are slices, and the pointer within the slice descriptor points to the same block of values, 1, 2, 3, which becomes the value 0, 2, 3. So when we change it through B, we've changed it through A. That's how slices work. And that's also how slices work as a parameter. Okay, so the mental model we have is that a slice is passed by reference, because usually what we're thinking about is the data in the slice. Okay, fine. Let's go on and do another thing like this. We're going to do this with maps. Okay, and I don't think I can use %p with a map, and it doesn't really matter. So we'll get rid of those. And I'm going to have a map. We'll call it M. It's going to be a map of int to int. And we'll just have like a 4, 1, and a 7, 2, and an 8, 3. And I'll hit format to put a little bit of space in there. And we're going to call this function with M. And then we're going to print it out again. Okay, fine. So I'm going to change M. I need to change M, right? It's going to take a map of int to int. And we're going to call that M1. And I'm going to go down here and change M1 to have the value 3, and we'll set the value of 3 to 0. Okay. And then I'm going to change M1 by doing a make. And we're going to print it out here also. So we're going to print it out the first time and the original. So my function is going to take the map and it's going to replace the map somehow and change it and print it out again. And when I run this, I'm not going to return anything, so let's take that out. Okay, let's try run it again. Like I say, I'm not returning a value. So let's do that one more time. All right, so the first thing we see is that M1 is a map with the value 4, key 4, value 4, when I printed it. But M is a map that still has these different values. So M started out with 3 keys, 4, 7, 8. And when we look at it after calling do, it had 3 keys, and now it has 4 keys because it has a key 3 with a value 0. So that's the result of this statement right here. The first statement in do assigns something to the map M1. Well, what's M1? M1 is the same map as M. In other words, it's 2 map descriptors and the same hash table. And the hash table that had 3 keys becomes a hash table with 4 keys, so M gets changed. Then M1 gets changed in a different way. I assign a new map into M1, and then I assign a key and value into that new map M1 and print it out. But when I return from the function, the original map M doesn't see any of that. So what's going on here, there's 2 things. First of all is the behavior of the map passed as a parameter is the same as the slice. Okay, and so when we change the map, the original map that was passed in as a parameter, so the formal parameter M1 has the value of the actual parameter M when we start. But then I change M1, I assign to it, and when I assign to M1, it doesn't change M in any way. And the reason for that is that we have to think about M1 as a local variable in the function. Okay? And in fact, that's what it is. The formal parameter of a function is a local variable to the function. It is initialized with the value passed in the actual parameter when the function is called. And after that, it's just a local variable. I can assign to it. Now, most of the time, I don't reassign to parameters because I think that creates more confusion. If I need to assign something, I'll create a new local variable. I do sometimes, but it's just one of those readability things. You don't necessarily want to go fiddling the parameter too much because then it's hard to remember, is that the original parameter value or is that something I changed in afterwards? Okay, so after that, M1, when I get down to these last 2 lines of do, M1 is a totally different map. It has no relationship to M whatsoever. And it's a map that's local to the function. So when I'm done with this function, that map is just going to go away. Right? Now, what happens if I want to replace the original map? So I'm going to make one more change to the function I've got right in front of me. And it could look a little weird because I'm going to change this so that M1 is a pointer to a map. Okay? Right? So the first thing I've got to go down here is when I call do, and I'm going to add another print line. So I'm going to print the value of M before and after I call the function. Right? When I call the function, instead of passing in M, I have to pass in the address of M. And the function will now take a map pointer, and the assignment then has to assign through the pointer. We haven't talked a lot about pointers, but I think this notation should be somewhat intuitive, right? M1 is a pointer, we dereference it to get the original thing that we're going to store into. It does cause one weird thing, and that is to use the pointer with the brackets as map indexing, we have to dereference the pointer first, and then we can actually work with it. And when I get down here, I will again need to dereference M1. If I didn't do that, it would just print the value of the pointer. If I want to print the map, well then I have to dereference it again, so I put the little star in front. So an asterisk in front takes the address, and a star in front uses that address to get to the original thing. So now when I run it, I'm going to see something quite different. Okay. M1, of course, that's my original map right here that I declared in the program. Okay, excuse me. And then M1 is a totally different map, right? Well, that's just the same as the last time. But now when I print M after calling do, I get the same map that I had in M1. So now what's going on is, this is a different kind of reference. So in the first case, when I passed a map by itself, the map descriptor gets copied, but I have a reference to the original hash table. In this case, what's in front of us right now is that I'm passing the address of the map descriptor, so that when I overwrite it on this line, I'm not only changing the map descriptor in do, I'm changing the map descriptor M in the main function also. It's getting overwritten. So at this point, when the function is done, M is the same map as M1, and the original M is gone, right? We assigned over top of it, all right? So it's as if I had changed M here. The do effectively is assigning to M, right? And so M becomes a different map, the map that we had in here, right? So all of this is trying to get to the idea about what's going on with parameters. I want to jump back to the slides now, okay? Because what I talked about was this notion of by value or by reference. And I want to just say, from a technical point of view, there's no such thing as by reference in Go. Every parameter is passed by value because the formal parameter is a local variable in the function. It gets assigned or copied the value of the actual parameter. And, if that value is a descriptor, for example, then yes, you're referring to something that was referred to from outside the function. Okay, so the slice descriptor gets copied into the slice descriptor of the parameter. The formal parameter is a slice descriptor. It gets copied the slice descriptor of the slice that was passed in. They both point to the same actual table of data in memory. So we think of slices as by reference, but the slice descriptor isn't by reference. The slice descriptor is copied. So then we saw the map, and the map descriptor was copied, but they both pointed to the same hash table. And then we have the third case where I pass a pointer to the map descriptor, and when I change that, if I change not the pointer, but if I change the map descriptor in the function, I'm also changing the map descriptor in the main function. So what we saw was the main function had its map changed. Not just a value inserted into the map, it became an entirely different map. Okay, so in Go, everything is passed by value. You pass an integer, you pass a string descriptor, you pass a struct by copying it, you pass an array by copying it, you pass a slice descriptor, but you're copying the slice descriptor, not the slice. You're copying the map descriptor, not the map. And so again, we think the mental model of slices and maps is by reference. But again, what we've actually done is we've copied the descriptor as a value parameter. And the fact that it is a descriptor means we're still referring to some outside data. Okay, I know that sounds a little complicated, but I want you to walk back through these examples I've shown you, because this is very important. It helps us understand how references work, and how a slice or a map is really a reference to underlying data. Because otherwise people are surprised, right? You pass a slice into a function, and the slice assigns to the function, and then suddenly you see that the slice is changed outside the function. Yes, because the slice descriptor is copied, but the underlying slice data is not. The map descriptor is copied, the underlying hash table is not. And if you want to actually copy it, that's a different problem altogether. Okay, so I want to move on for a second and just talk about return values. And we've already seen this a little bit. Go allows one or more return values on a function. So I can have a function that returns an int, or I can have a function that returns, say, a file pointer and an error. And the only difference is that when you do two returns, you have to put parentheses around them, right? So one return type can sit here by itself, but two return types, they get parenthesized, okay? And when you return, of course, you've got to return all the values. So if I have a function that returns an int, I need to return the int in the return statement. But if it returns two values, then my return statement will have two values. And that, you just have to remember that, because you'll write a function where you'll return a pointer and an error, and the first two or three things you'll do is you'll figure out what the errors are. And you just have to remember you're going to return like nil and some real error. And then you get to the end of the function and you return, a real pointer and no error. Okay? But the ability to return multiple values is extremely convenient in Go. the one last thing I want to talk about functions, and I just want to mention it, is Go does allow recursion. All modern languages pretty much do. That is to say, a function can call itself. And that's very straightforward and it's useful. Now, here's an important thought. Anything that you can do by a recursive function can be done with a for loop without recursion. The only difference is that sometimes when you write it with the for loop, you're going to have to do a bunch of bookkeeping, which if you do it recursively, the bookkeeping is done for you by this whole concept of the call stack. And I want to illustrate that very quickly. So when I call a function, right, I have this, my process lives in some memory, right? That memory includes, for example, the heap, and the heap is where we do things that are allocated, they're not on the stack, right? But I have the stack, and I have some function A, and A calls B, and when we call B, the stack extends itself downwards, and we get a new stack frame for B with its local variables and parameters. If we call another one, we get C. And when we're done with function C, well, we remove C off the stack, and we're left with B. And when B returns, then the stack frame for B goes away, and we're left with the stack frame for A. Fine. So if you have a recursive function, all that means is you get a stack frame for A and it calls itself, you get another stack frame for A, it calls itself. And the nice thing about this is that a certain amount of bookkeeping then is being done for you by these invisible stack frames that are created by the process of calling itself. And if you didn't have a recursive function, then some of that bookkeeping you might actually have to do in your own code in the function that's using a for loop to do iteratively what you can do recursively. So recursion is almost always slower than iteration because recursion needs to create all these stack frames. But in some cases, and here's a good case, couple of cases for you, tree and graph data structures. So when you walk a tree or a graph, writing the recursive function is just so much more natural and easier to understand than trying to do something else, right? And in the end, what's best is to write things that are readable and understandable, even if they're not super, super efficient. Because the long-term value is that we can understand them and modify them and fix them and so on. So the only catch to recursion is if we're going to do it's just like a loop, right? If I write a for loop, my for loop needs to stop. I need to get to some condition where we stop. And if I'm doing recursion, the same thing. I have to have a stopping condition. If I think about a tree structure, of course, I've got some tree and it's got nodes and nodes under nodes, but eventually I get to the point where the children don't exist and I have maybe a nil pointer. And that's what I'm showing here, right? So if I'm going to get to a nil pointer, that allows me to have a stopping condition that says, okay, just stop and return, don't try to call any further. And as long as I have a well thought out stopping condition, then recursion is perfectly safe, okay? There's the problem of infinite recursion where you don't, and then you recurse until the stack grows so far down here there's no room for it, and then your program crashes. Okay, so recursion is a very useful thing in functions. Again, if you're a functional programmer, you work with a functional programming language, recursion is very natural. Okay, in a traditional language, recursion is still useful. It's not as efficient as doing things other ways, but it's very natural sometimes depending on the kind of program you're going to write to use recursion. Okay, so now I want to talk about the defer statement. And the defer statement is actually kind of a new contribution of the Go language. All right, and it has to do with the fact that sometimes we want to make sure things happen, right? If I open a socket, I need to make sure I close it, right? If I lock a mutex, I want to make sure I unlock it. And in a function, sometimes there's many ways out of a function, right? I go into a function, I lock a mutex, and then there's some logic, and there's different places I might return. And then somebody else, so I mark all those places where I unlock the mutex, and then somebody else comes and modifies the function, and they add another thing into it, and they forget to unlock the mutex, and then the program blows up. Okay, so defer is a way of saying, hey, at this point, I know there's something I need to do when I leave the function, and I'm going to record that right now, and then you'll do it when the function exits, wherever it exits. And that actually means we can write less code and cleaner code. Now, that all sounds good, so I need to show you what this actually looks like. Right? So here's a little function that opens a file, and what we're going to do is write a defer, and the defer takes a function call. okay, it's like you call the function, in this case f.close, and we freeze dry it and we store it. And when we get to the end of main, down here at this closing brace, then we take it out and warm it up and execute it. Okay? Now, typically when we have something like this, I open a file and I check to make sure the file was really opened, because I can't close the file if it didn't open. So once I've checked the error and handled the error, the very next thing I do is I defer the closing. Okay? What happens is that close is guaranteed to run at function exit. It doesn't matter which return statement got me out of the function. The fact that I leave the function, the defer will execute. And if I have more than one defer, so let's suppose I have a defer A, and then I have a defer B, when I leave the function, they'll be done in the opposite order. So defer B will be called and then A will be called. So they get stacked up, right? And they just, whatever the last one in is the first one out. So defer is extremely useful. Defer operates on a function scope, okay, not on a block scope. So if I look at this code right in front of me, it's good that it does that. So I have a function where I start off with my default file is going to be standard in. But if you give me a file on the command line, and I can open it, then I'm going to use it instead, and then I need to close it, because I don't need to close standard in, but if I open some other file, it's my responsibility to close it, right? And so the close here, this defer, depends on doing the things in the if statement, and if I didn't do them, then I won't do the defer. Now, if defer were block scoped, if it executed at the end of the nearest block, it would execute right here, and it would close the file before I even use it. So defer operates at function scope. Okay? It doesn't matter how long I spend in the function, the defer will happen when the function exits, and only when the function exits. All right, so that's the good part. I want to show you an example of where it's not going to be useful. And you know, I've had several example programs already where I've gone through the command line arguments. I've opened files, and I haven't used defer. Well, first of all, I hadn't introduced it, and I didn't want to talk about it, but it wasn't going to be useful there. So here's a for loop, and in my for loop, I'm opening a bunch of files, and after I open them, I'm deferring closing them. When will those closes happen? And the answer is they will not happen at the end of the for loop. So it's not like I open the file, I do some work in the for loop, and then close happens when the for loop is done. Instead, the closes don't happen until the function is done, because again, defer is based on function scope. So in the code that I'm showing you right here, it's a little bit of a problem, because if I open up enough files, I won't have closed them until too late. Okay? Most operating systems have a limit on how many files a program can have open at any one time. It may be big, but let's just suppose I can pass in a very large list of files. And I start opening and opening and opening, and I defer closing, and I defer closing, right? And they don't actually get closed. And at some point, I end up with, say, 1,000 files open, and then my program crashes because it hits the limit. So this is a case where defer is not useful, because what I really need to do is when I get to the bottom of my for loop, right here somewhere, at the bottom of my for loop, I need to just go ahead and do f.close by hand. I don't want to defer it to the end of the function call, I want to execute it at the end of the loop. I open a file, I use the file, I close the file, I start my loop over again, and now the number of open file descriptors is going to be very small, which is good. All right, it's just good for the health of my program. Okay, so that's kind of a gotcha with defer. You just have to remember that defer is a function scoped thing, and it doesn't do anything until you get to the end of the function. So there's one other thing with defer. It's sort of a gotcha, not exactly. It's very important to realize that the value in the function call you're deferring is copied. Okay, so I have this function where I set A to 10, and I defer printing it, and then I set A to 11, and then I print, and I'm printing the A that's 11, and then I exit the function, which means the other print, the deferred print, happens. All right, and so first it prints 11, and then it prints 10. And it prints 10 because 10 is the value that A had when I deferred the call. Okay, so what's happening is when I call this function to defer it, is Go is actually setting up the parameters based on the values of things right then. And so ints are copied, and so it's setting up a call stack for the deferred function with the value of a at that moment. Okay, so when the defer happens, when the defer actually calls the function down here at the end, it's already got that value of a captured. And so it prints 10, not 11, because 10 was what a had at the time of the defer. Okay, it's very important to realize that. Now, when does it actually happen? And I've got one more illustration, which is going to show two things. The first is, this is important. So defer, again, can only defer a function call. But let's suppose there's something I want to do that's not really a function call. I just want to assign to a variable or something like that. It's not already a function call. I have to turn it into one. And so what I'm actually showing here is defer is going to call an anonymous function, and I've just written a function literal right in my code, and I've added a pair of parentheses. So I've created this anonymous function, and I've called it, and then I've captured that call right here with defer. Okay, and inside that function I have whatever statements I want to. So I have this thing that says like a is equal to 2. Now there's another thing going on here, and you'll see this occasionally, and that is I have a named return value, right? So obviously parameters to a function can have names. They need to, or they're not very useful. But you can also give names to a return value. And when you do that, it also becomes like a local variable to the function, and you can assign to it inside the function. And if you do that, you can have what's called a naked return. I have a return statement that's not returning any value, and I don't need to because I named my return value. Now, this is not the best style, and I don't recommend it. I'm just showing that it can happen. And I'm just showing it this way because I'm assigning 1 to a, and then I'm deferring a function call that assigns 2 to a. And the question is, what comes back from the function? And the answer is what comes back is the value 2, right? As soon as I hit this return statement, I'm leaving the function do it. And when I leave the function do it, I now start to execute the defer stack. And the defer stack has this anonymous function whose job it is to assign 2 to a. And what is a? Well, a is the return value of the function. So I assigned 1 to a, and then I started returning, and magically my return value got modified to be 2. And then the return is done, and whoever called do it sees the value 2. And that's basically it. That's defer. You'll see more examples of it as we go along, and it'll make more sense when you see it in a bit more context. But the kind of things that I would typically do with defer, like unlocking a mutex, well, we really haven't talked about mutexes yet, so you haven't seen that kind of code. Okay, so that's this little segment on functions. I wanted to introduce what functions can do in Go, how parameters work, because I think that's very important to really understand how parameters work. It helps eliminate some surprises about what changed in my data. And then I introduced the defer statement, where the defer statement is just a very handy utility in Go to make your code safer. And you'll see some examples of that as we go. So that was the first part of my two-part segment on functions. These are sort of the simple functions. And the next segment we're going to talk about closures, which are a particular kind of function call that's encapsulated inside another function.